in a group, numbers are integer. Within the group. Is I maintain but no relation has inside of group equal to point. We want it to be has consider that the star star associated. Does E have an inverse? E. Doesn't do much. We're going to call it the trivial of G. We always had the right? No set you were looking at. These are like you can take every thing you can. The group has to be empty. Be just the. So let's consider what other types of subgroups we've already seen. We've seen the integers in fields. Well, in the same way, I could think of the fractions. Not plus, there. The rational numbers, again under addition, would still be a group of the reals. We did complex. So I could think of the unit multiplication, a group of complex numbers excluding 0 under multiplication. Because if I have 0, then I don't have an inverse for 0. And so when we're doing multiplication, we throw out 0. As a matter of fact, I could There are infinitely many other groups. Somebody pick a number. So think of U7. Wasn't that a homework problem dealing with U7? Is a sub. If U7 is in U, it's all. So we have a chain of subs. And you put any number there U6, U14, U123, 123rd roots 4. Problem you did with the table had a set of matrices, right? Those matrices behave. The group of size 4 by filling out which one. But in that sense, that particular group of matrices was a set of the whole matrices. All right, now I'm going to stretch my brain. 1, 0, 0, 1, negative 1, 0, 1, 0, 1, 1, 0, and then negative 1, 0, 1, negative 1, 0 is a set of GL2R. Through the active matrix multiplication called that the general group of size 2, called the general group size n matrices. I've seen lots of subgroups, but I like. So let me go back to the size 4. Look a little more closely. I had to come up, and we said out of the tables you could make, you put an E, a B, or a C. You got 2 different tables for isomorphic. Those 2 tables really like the following. This is the one, E, B, E, B. The other had E's all the way down the diagonal. And as soon as you put an E there, you were forced to put a C here, so 1 of each type in each row and column, and a B here, and thus an A and an A. Groups are not isomorphic because the way it behaves over here on the left is not the same way that the operation behaves. V. Why am I calling it? Because when Klein wrote about this, he the 4 group. Who's taking German?
Eins, zwei, drei, vier.
Wir. Starts with a V. The 4 eine Wir-Gruppe. The Klein. Okay. in both groups, I have the whole group. I have the group that contains just the A. So, on the right, the whole group and the identity. What else do I have? That's closed, right? Group in and of itself, it's got to be closed. So pick a number. You want to do Z first. Okay, if I'm in Z4, pick something that isn't 0.
2.
Okay, let's look what happens and do the operation with 0. Or do 2. If I just look at this, within this, I get isn't that what we did in ones? Order 2. It's closed. It's associated because the before was associated. Got an identity, and every element has a inverse. 2 is its own inverse. Okay, then what else? I always keep putting 0 in. I have the identity in a group, right? And if I want a subgroup, it better get identity from the group. What happens if I do 3? Set. There's only one other option, right? For sets of size 2, you pick 1. What happens? I said neither of those is closed. Pick a set of size 3. Leave one of the numbers out. I'll leave out 3. But then I have 1 and 3. Right? What's 3?
6. That'll be. Or is it?
But you just said I should leave 2, didn't you?
Yeah.
Leave out 3, then I have 1 plus 2. Crap. If I leave out 1, what's 2 plus 3? There's no that stays.
That just in Z4.
Interesting criteria. The moment I'm only looking at things in Z4. Closed. Now gone through the entire power set of elements. 1, 2, 3, 4, 5, 7, 8. They're all the 8 possible that we could have. And only 3, the whole group, and Z2, this 0 thing. So really, there were only 3 groups here. And if I think about containment, the biggest one is the whole. Then 0, 2, and just 0. Make a hierarchy that looks like this. That's called a subgroup diagram for Z4. Groups. There are 6 other possible things. Subgroups of size 2 or subgroups of size 3. Which do you want to do?
So E and A.
E and A. So again, if I think of E, upper 4, look, that's closed, isn't it? A times A gives me E, E times A gives me A. That works. Be associated because the one above it was associated. It inherits associativity. It's closed. An inverse because A is its own inverse. Well, there for size 2. So pick one of them.
It's going to be EB.
What happens then? B is E. EB is B. BE is B. Wait a minute. That's the same. What about ah? Here's another way I know 2 groups are fundamentally different. Z4 only has 2 proper subsets. V has 4 so far. EB, EC, just. What about the I did left one out?
Leave out C.
If I leave out C, I've got E and A and B. What's AB? Crap. So if I leave out C, then it's not closed. What about B? Then I've got A and B. What's AC? All right, let's try leaving out A. Then I've got B and C. What's BC? Crack. So it turns out proper subgroups here, what's my going to look like this time? The diagram changes because the diagram is containment. So I have the whole top. I have EA, which is a subgroup of the whole thing, a subgroup of that. I have EB, again, sort of containment. I have EC, and this sort of containment. Line 4 group. If I want structures to be the same, isomorphic in all their parts of the interior, I see differences. I know I have a problem. Those two things keep the same. So in spite of the fact that I have order 4, group of order comes in 2 flavors. Side of the client, or it's Z. They're distinct from one another. So I did a group of 3, the group of order 2 was 1 and 0. Okay, in one sense, we really built this a little our subset, and this subset qualify as a group. Then is a subgroup if H is closed. We're using the same operation. H has to be the same as the identity in. Because if H is a different identity, then you have 2 identities in it. There's only 1. And it has to contain inverses. And that's a way I can tell apart the Klein and Z4. In the Z4 group, we had the zone inverse. We had all 4 E down the diagonal, didn't we? But in Z2, 2 of them were their inverses. Totally different structures. I'm going back to happier about that because that's less. Let's consider the set of differentials. Is a group of F. The answer to this question can be found in calculus in the very first results. If D addition. Why?
You can add
Derivatives.
Ah, the sum rule for taking derivatives. All prime is F prime. So if F is differential everywhere, D is differential everywhere, still differential everywhere. To a function that doesn't, and that's function 0 everywhere. That's a constant. Constant differentiable.
Yeah, sorry.
0, right? It's 103, or the constant. The derivative of 0 is a horizontal line. It's got a slope. So that F in our subgroup. That's part 2. Pick a function you know everywhere.
X.
Okay? What and is intangible to, as a matter of fact, if you took function F, its in would be minus, and that's a constant times F, which means chapter 1 of the calc book. Y'all did that.
Like,
Yes. My Z is on purpose. So question. Quite frequently, especially in chemistry, a lot. There's a bunch of this in aerospace engineering. But if I think of matrix multiplication, then it turns out for me to look at things closed, that's actually kind of looking in the set of matrices at a lot of very unusual subgroups. Most is the set of matrices whose determinant isn't linear yet. Sit on it for a little while. The following theorem in the textbook is stated. A non-empty set A in a group for all H. H in the textbook. If I want to know about H, that work. This is another, the proof is literal definitions, but it's actually like 4 lines. And if and only, prove an if and only. Suppose H is a subgroup. And elements of H, then B is that's a property in a subgroup. You have to have all the inverses, right? Property is you have to have closure. So A is in H, B is in H, so B inverse. And so by closure, AB inverse is in H. Check mark. I'm done. Means I have to start with A versus an H for all AB, and all 3 properties. And H. AB and start with A being an H. Then A H. Well, what's A inverse? Yeah. This property, the identity number property 2. Wait a minute, if the identity is an H, then E E times H. E H and A inverse A, E A inverse, that means that A inverse must be H. There's for every element its inverse. And then if I have A and I have some other inverse of something, well, that means that A and H, there's actually get all three of these from the inverse. But again, going through and enumerating all of this stuff is a pain in the ass. And it turns out all the time that closure is enough. Theorems boil down to the same results. All I really have, think about it, inclined forward, all we did for Z4. Okay, when I said that 3 never, you said, why is it not 3? And I said it was part of the fact that we were in, right? Different. Life easy for them. Let's use the clock. D12. Model. Take 3. Subgroup that 3. It must contain at least the number must it contain. Zero. It's got to contain the identity. So it must at least contain those. Could I start looking at closure? Closure is enough. So what can you make? So I need 6, right? Closed. There's 3 and 3 is 7. Keep going. What else do I have to have? Now I have 6. I better have. Well, now I have 0, 3, 6. What else do I have to have? 12 is 0. Doesn't matter. Put little 12 of these additions. Apologize. So
I said 1 because I missed a Z 12.
0 as opposed to. Let's start adding. Okay, so I didn't get anything. What about? I didn't get anything new there. 9 and 9. I think I've got it closed. I think if I 0, 3, 6, and 9, that stays. Add 0 to any of those, something in there. You add 3 to something in there. You add 6. You add there. That's a closed. We built this group. Does it have closed? It's associated. Does it contain? Yes. It's there at the beginning. Does it have an inverse?
And then plus 3 is here.
Every element has an inverse. As a matter of fact, it's not just any group. It's the smallest possible that's going to have 3. So the must the way 3 as opposed to 12. I didn't.
What?
Oh, let's see what happens. 5. I need the identity. The identity element. Building block. I'm going to call that generator of subgroup. Way. Okay. Right, I get, I see 3. I'm going to 6 and 9 eventually, probably, right? What? 8. 8 and 5 gives me 1. 1 and 5 gives me 6. Hey, 6 shows.
11.
There's 9 left. I would. Gives me
0.
elements, didn't I? Smallest possible in is all of Z12. So there are 5. None. We did this by repeatedly adding. Yes. Repeatedly adding because we were in a group whose operation was multiplication. By multiplying. And you did on your homework. Complex numbers under multiplication. Roots of unity 7. We started with this one. The problem somehow, right? We were isomorphism. So let me give this the text called it 1 root. I want to make more the identity, right? What's the identity? 1. Fine. Identity is what I build itself. I added 5 to 5. I'm gonna multiply even 2 pi over 7. Complex numbers. One of 2 things is evident from you really hate complex numbers. This homework just gave it to me. What do you do here? You add the angles. So there's my next. I cube that beta 1 squared times zeta. What do I get then? And the one after and the one after that. One after that.
Pi I over 7.
2 pi I, right? Sine of 2 is 1. Pi is 0. We've got 1, 2, 3, 4, 5, 7, all 7. With 1, we built the rest. We generated this. So much I'm going to generate. I'm going to generalize generating. A group, a element G, then a raised to n power n. Got to contain the identity. It's got to be closed because 2 powers multiply them together. You to the minus n, and so you get the identity. Not only that, subgroup of G that can. And we saw that when we looked at 5. We saw 3. I said, oh, we're going to get 6 and 9. And then we did. I could make from 3 have to be in there. I'm going to call this the subgroup by A. A. One other adjective for this cycle.
That last one.
Isn't it? draw a clock on a piece of paper. Well, no, but 3, 6, clock. I go an exact 5, bouncing around the clock 5, aren't I? Around the circle, which is the identity. Which is why I like being unit circle pieces. Full collection Z12. I got is cyclic. A J group if when I do so I is J 5 because we got the whole thing right. Say that using under multiplication to the 2. Those are both cyclic groups. A cyclic group of order 12, a cyclic group of. As a matter of fact, every Zn talk about the integers not 1. Technically, it's even more boring. With cyclic, I have to be able to do whatever you want, bigger than 1. And then start adding 1 over and over. Eventually, you get whatever number you. Z14. 1 and 1 is 2. Adding mod 4. Add 1, I've got all. Matter of fact, under addition is cyclic. It's never around. But I think about generating from 1. I wouldn't the identity, but I can get the identity inverses of that. I get all the negative numbers. And then closure and identity generated. I like cyclic groups. You have to know what one thing is to generate the whole thing. Is the group cyclic? But if that's
So
what happens when I start multiplying A by A by stuck between A. If I pick B and C, all of this back here, no single generate. A generated by B contains two things. Contains four. B only contains. I can't get all four. So in fact, that it looks for easy group. I don't want to simple. Not simple. U and Z7 isomorphic. Yes. And Zn are isomorphic. The root is generated. And we know Zn has a generator. Values of n. That's primitive of unity. Cyclic groups. We can and I'm basing the idea of going around a circle. Itself is twofold. One, in U it to generate. In Z, I can the identity. But in U, there's no to start with, right? Smallest thing. An infimum of had to tie that. I'll be like, why am I this crap? It's useful. If I want to find of the unit circle is the angle above that. I'll only of that. I'll miss angles. Really like. I want to understand. And maybe I can answer Jay a little bit better. Oh, there is some weird about different 12. I hope you all have a wonderful rest of